Good day everyone! For today's video, we will going to tackle some information entitled in Module 6, Section 3, Weighted Graphs. So, what is weighted graphs all about? Weighted graphs is a graph with edges labeled by numbers, which is called weights. In general, we only consider non-negative edge weights. Sometimes infinity can also be allowed as a weight, which in optimization problems generally means we must or may not use that edge. And for the example, the weight of an edge can represent first, cost or distance, the amount of effort needed to travel from one place to another. Then the second is the capacity, the maximum amount of flow that can be transported from one place to another. So, representing a weighted graphs using adjacency list. So first, each node in the adjacency graph will contain. Second, a neighbor node ID, which is this field was already discussed previously. So the third one is the cost field, which is this field is new. Okay, for the explanation, the row 0 contains the linked list with the following three elements. First, nodal is equal to 1, link cost is equal to 3, which is this represent the link of 0 and 1. Second, nodal is equal to 3, link cost is equal to 2. This represent the link 0 and 3 in the figure above. So the third one is the nodal is equal to 8, link cost is equal to 4, which is this represent the link 0 and 8 in the figure above. So, representing a weighted graphs using an adjacency array. If there is no edge between node I and node G, the value of the array element is A, I, and J is equal to some very large value. Otherwise, A, I, and J is a floating value that is equal to the weight of the edge I and J.
In this presentation, we are going to look at weighted graphs as part of our graph theory series. Now, in particular, what we're going to do here is to write the adjacency matrix for the following weighted graph. Okay, so we have 6 vertices there. They are all have degree 3. And so what we're going to do is write out the adjacency matrix for these. And on the adjacency matrix, rather than the fact that they are connected or not connected, what we're going to do is the weighting. We're going to indicate the weighting of the edge between each vertex. So V1, V2, V3, V4, V5, and V6. Not exactly necessary to put in the row names and column names of adjacency matrix, but it actually just is helpful when you're just getting started. Again, V1, V2, V3, V4, V5, and V6. Okay, so let's look at vertex 1. It's not connected to itself. Okay, it's 0 there. It is connected to vertex 2, and therefore we're going to put a 2 there because the weighting of that edge is 2. So it is the entry for the adjacency matrix is 2. It's not connected to vertex 3, so we're going to have a 0 there. Now, it is connected to vertex 4, and you have to be a little bit careful when you're reading the graph that this edge here is vertex 4. So I'm just going to sort of indicate which of these are connected to which. So that 3 is there is connected to that edge, that 3 there is connected to that edge, and that 4 there is connected to that edge. So that is the weighting from V1 to V4. So there's a 4 there. So the next thing we're going to do is it connected to V5? No, it's not. What about V6? Yes, it is connected to V6 with a weighting of 8. Okay. Now we've seen previously that V1 and V2 are connected to each other with the edge of that has weight 2, and that actually works in reverse. So V2 is actually connected to V1 the same way. Again, it's the one right up here up at the top. And in fact, they all are. So what I'm actually going to do right now, to save time, is I'm going to sort of write this row, the first row, along the first column, because there's a symmetric quality of what we're doing here. 0, 2, 0, 4, 0, 8. So symmetric quality means if V1 is connected to V4, that means V4 is connected to V1. And if V5 is not connected to V1, V1 is not connected to V5, and so on. So we have the first one there for V2. So we're just going to work on the second row now here. And we have the first one for V2. It's also connected to V3. It's not connected to itself, so 0 there. And it is connected to V3 with this 5 here. So 5. It's not connected to V4, 0. It is connected to V5 with that edge of weighting 3, this one here. So that is a 3 and a 0. It's not connected to V6. And again, what we can do is write the second row along the second column. So we already have the first two entries there, so we just have to complete it. 5, 0, 3, 0. And again, it's to do with the symmetric quality of an edge. If V1 is connected to V2, then V2 is connected to V1. So V3, we've already got it's not connected to V1. It is connected to V2 with degree 5, with an edge of weighting 5. It's not connected to itself. It's connected to V4 with an edge weighting of 7. It is not connected to V5, but it is connected to V6 with an edge with weight 3. And once again, write that along the bottom, or along the column, the third column. Things start to work very quickly once you recognize that symmetry quality. Now we're going to look at V4. It's connected to V1 with a weighting of 4, the V2 with no edge. It's connected to V3 with a weighting of 7. It's not connected to itself. It is connected to V5, so we have a 2 there, because the weighting is 2, and it's not connected to V6. Once again, 2 and 0. Now, V5, it's not connected to V1. It is connected to V2 with a weighting of 3. Not connected to V3. It is connected to V4 with a weighting of 2. It's not connected to itself, so we're going to put in a 0 here. And finally, it's connected to V6 with a weighting of 6. And again, we'll put in 6 here. And finally, V6, the only thing we have to do now is V6 connected to itself. No, it's not. So that is the adjacency matrix for the weighted graph. What I'm going to do now is just sort of present the answers a bit more clearly. There is the adjacency matrix there with the proper notation for the A of G as well. So that's what the answer should look like. Okay, and in terms of proper presentation, the V1, V2 thing, I know at the top of the last slide was just to sort of help guide the eye. Those column names and row names, they were just had to help guide the eye. They're not actually really necessary. Okay, that ends our presentation.
Hi there, thanks for returning here. We're having a look at a section on drawing a network diagram, and this one specifically is drawing weighted graphs from a table. This is going to be kind of fun. So drawing weighted graphs from a table, there's our table over here. It's got A, B, C's and D's, and it's got weights down there. They might be 4 towns and distances apart. They could be a whole bunch of things. But let's express them. Let's see if we can express it in a weighted graph from that table. So our headings are going to become our vertices. So we're going to have vertices A, B, C and D, and we're going to try and arrange them so that they're the right distances apart. But it does get tricky. I think I'd rather go from a weighted graph back to a table. But anyway, we'll be brave here. Cell values, so the numbers in the cells there, they become edges, or the weightings on the edges anyway. So here we have our diagram. I've cut to the chase here. Here's one I prepared earlier. But we're going to double check and give you confidence that this is all in a reasonable arrangement. It might not be exactly to scale, but give me a break here. But let's have a look at the different information that is in the table and see if we've represented it in a weighted graph here, just quickly. So here, this cell here tells me that A and B are both vertices and they are 18 apart. And we're going to have a spaghetti diagram here. But that 18 is represented on that weighted edge there between A and B. And you have one over here as well of the same size, because on our table, if we go from B to A, we're going to be going the same distance, aren't we, if they're distances. So let's have a look at here. Now this indicates this cell here is between C, although I've written over it, and A, and it says it should have a weighting of 10. So if we go down to our diagram, we have an edge between A and C that is 10. Right there. And we have AD being 17. Let's see where we can spot that. It's actually inside there. It's one of the diagonals. The joining edge from vertex A to vertex D is one of the diagonals there, and that's 17 long. So if I could continue here, I guess, but let's have a look at one more. C to D is supposed to be 8 here. C to D, and let's have a look. C to D is 8. So I think you'll agree, I hope you'll agree, that this diagram I prepared earlier is a good representation of the information in the table. So our headings, our A, B, C's and D's here, our headings for our columns and our rows, they became our vertices, and our values in each of the cells, our number values in there, they became the edges, or the lengths of the edges, the weightings on the edges. So that's a weighted graph from a table. I hope that makes sense. It seems to make sense to me, but if you stare at it long enough, I'm sure it will. Thanks for listening. Hope you can try one for yourself someday. And I'll see you next time.
So that's all for today. Thank you for listening. Goodbye and God bless.